This meeting is being recorded.
Okay, recording has started. And now we have the first technical class. Last week was technical, but now we actually really start the technical content. This week is software, it's design tools. And then next week we get in labs and start making things. So this is about CAD, how you're going to design what you make. I'm going to cover 2D, 3D, and then media and a bit on AI tools. And then the assignment is to model your final project. The final project can change, but the goal is to go through the exercise of modeling it. And by model, I want you to do it as many ways as possible. So raster and vector, which I'll explain, 2D and 3D, render it, animate, simulate it, as many ways as possible. Then you're going to compress your images and videos, and you're going to put them on the class page. Each week, I'll link featured assignments, one or more. This week, it's Nadia, who was one of the best documenters ever in Fab Academy. Her final project was this cool interactive game. And here's a video of dropping puzzle pieces on it. Here's a rendering of it. And then if we go through, she used just about every tool I'm going to talk about. Excuse me. And more and more and more. And so she explored every possible tool. This goes beyond the minimum needed each week, but is a great example of the range of tools available and the exploration you can do this week. So that's Nadia's example. Okay, so to start, 2D is flat, 3D is volume. And we're going to have tools that work in both 2D and 3D. So you'll need both 2D and 3D tools. In 2D, you can both raster and scan. Raster is with pixels, discrete dots. And so, for example, in the electronics week, we'll cover electronics design tools. But this was the student who was a good artist. And sorry, I hear background noise. I'm going to mute everyone. Unmute when you want to talk. He was a good artist, and just for fun, by eye, he drew a circuit diagram. He then scanned it in, and then using the workflows you'll be learning, he actually produced it just from the hand-drawn drawing. I don't recommend that for electronics, but it's an interesting, expressive workflow. Each week, I'm going to describe a range of tools that include both open source ones and commercial ones. Let's see, a participant changed the language. Don't do that. I want to figure out how to turn off languages. It's a global setting, so keep the language caption in English. I'll see if I can turn off participants changing that. So I'm going to cover both open source and commercial tools, and there's trade-offs in each of them. Sorry, somebody keeps changing the caption language. I'll have to figure out how to disable users doing that. Please don't change that. So I'm going to cover both open source and commercial tools. There's trade-offs. There's roles for each of them. For working with images, GIMP is freely available cross-platform tool that lets you open, edit, do anything possible with images. BIMP is an extension to GIMP for working in batches, and I'll talk about that when I get to compression. And so here I am in GIMP. I'm going to make a new image, and then I can open an image. Here I'm editing. I made a border. I'll pour some paint in it. I'll make another border and pour a different color paint. And then right now it looks like a shape, but if I zoom in, eventually you'll see the pixels, that these are individual dots. And so this makes sense if you're doing something that starts from an image or is best done by drawing and painting. Photoshop is a powerful commercial tool comparable to GIMP. My Paint is a really nice painting tool. It's an open source tool that emulates how a paintbrush works with different sort of ink and different sort of paper. And then Image Magic is a very powerful tool for not editing, but coding. So it can convert any image to any format, and it can do all sorts of operations on the images. And so now we come to this small but important page, which is the images you're going to post should be at web resolution. So they don't need more pixels than the screen, and then they can be compressed. So images web resolution are, say tens of kilobytes, maybe 100 kilobytes. A state-of-the-art camera can take images where the raw image is gigabytes. So images larger than that take up unnecessary space on the server, but more than that, they also take up, they're much slower to load. It makes your page sluggish. So your raw images need to be compressed down to post them on your site. So Image Magic lets you do all sorts of operations. JPEGs are compressed. PNGs are uncompressed. Compression makes it perceptually look right, but it can mess with the pixel values. So that's good for compression. It's bad for engineering. So in some places, we're going to use PNGs as engineering files, images as engineering files. In that case, we use PNGs. When we use them for visual documentation, we use JPEGs. But PNGs take up much more space than JPEGs. That's why it's important to distinguish. So using Image Magic, and again, when I show you these commands, let's see, Alto's noting WebP is also getting more popular. When I show you these commands in Linux or Mac, you can just do this from a terminal. And again, if you're using Windows, I recommend installing Windows Subsystem for Linux, and then you get them all that way. So this will convert a PNG to a JPEG. This will take a whole directory and convert all the PNGs to JPEGs. This, for example, will convert an SVG to a PNG. It lets you pick the density, the dots per inch. This lets you take the raw image, sets the compression to 50%, and resizes the image. And then this lets you do it with a whole directory. So you don't want more pixels than the resolution of the screen. And you can compress down significantly and have it look the same. So these are all utilities with Image Magic you can use to compress the images. You can do it one at a time in GIMP, but this lets you do it as a batch operation. And then again, BIMP is a GIMP extension to do batch operations on groups of files. So one of the assignments for this week is to compress your images and videos, and those are a series of codes for doing that. So that's raster. Vector is, instead of dots, you draw lines. This is a tool to go from raster to vector. Mods knows how to do that. Mods is something I originally wrote. It's now a community project. And if you read in an image, it knows how to read the image and trace it to find the boundary, and then send that to a vector cutting tool. Inkscape knows how to do that. Inkscape is a freely available cross-platform vector drawing tool. It's based around SVG, which is a really nice vector format. And so here I am in Inkscape. I'll do something similar to what I did in GIMP. So I'm going to take two shapes, and now I'm going to do what's called a Boolean operation. That's where you do logic on shapes. So I'm going to, I can add, subtract, intersect, difference. Here I'm going to take a difference. So I just subtracted one shape from another shape. Now, once I subtract it, it's gone. But what I'm going to do next is what's called cloning. So first I'm going to align these two shapes. Then I'm going to, instead of copying, I'm going to make a clone. And the clone means it stays linked. Here I'm changing the color. Now, if I change one of them, the other one changes. That's going to be essential next week for laser cutting, because you're going to make slots, and the slot is a parameter that depends on the thickness of the cardboard. And so if you have slightly thicker cardboard, you need to change all of your slots, and you don't want to go back and edit everyone by hand. So this is sort of rudimentary CAD in Inkscape. Illustrator is a commercial vector drawing tool. Sketchpad is a nice web vector drawing tool. You'll see me use that a lot for my examples. And then FreeCAD is a very important tool we'll be talking a lot about. The worst part of FreeCAD is the name that makes it sound simple and crude. It's a very powerful modeling tool, and it has parts of it work in both 2D and 3D. So here I am in FreeCAD. In 2D, you make sketches, and this looks a little bit like a familiar drawing tool like Inkscape, but is very different because it can do what's called constraint solving. So I'm going to make a sketch. So here's a shape. Then these are going to be the cutouts. And let me jump ahead to visualize. In next week's class, where we cover the vinyl cutter and the laser cutter, for the laser cutter, you're going to be making a press fit construction kit. So here's an example of parts cut out in cardboard that snap together. And the joints, the tolerance is very close. It has to be within a few thousandths of an inch. And so you need to globally describe the joint shape in your design. And you're going to need to do that for next week's assignment. So coming back here, so those are going to be my cutouts. I'm now going to trim. And so what it's doing is it's finding the intersections and it's removing the parts around the intersections. Okay, so I made the slots. Now, if I edit the slot, nothing changes. But now what I'm going to do is I'm going to start setting up constraints. So all of these points here, all of these points are, you can align vertically, horizontally, parallel, perpendicular, tangent, angle, point on point. Alexis, I just muted you. Enterprise is recommending Procreate on Apple devices. Yeah, it's good to mention that. That's very popular if you're in Apple ecosystem. So I'm going to start setting up relationships. So I'm going to pick that segment. I'm going to pick another segment, and then I'm going to do an equality constraint that says they should be the same length. So now if I edit one, the other one changes. Now I'm going to make those equal. Then I'm going to make these ones equal. So now the slots are equal and they're centered. And now I'm going to add a dimension constraint where I give it a size. So now I've got a dimension, and if I edit that one dimension, the whole part adjusts around it. So this was our first example of a parametric design. And parametric is one of the key terms. So in the computer cutting assignment, you need to make a parametric kit. What that means is you have one parameter, which is the slot size, and then the whole design adjusts around that. And so here's an example of doing that in 2D with FreeCAD. So now we're going to go to 3D. 3D is a much bigger universe of options. Let's see, I think this was, oh, right, yeah, this was a link to computer graphics reference. This was a link to one of my student theses where he talks about 3D representation. So a 3D design tool has to do much more. So when you design a jumbo jet, there's a lot of steps that go into the design. And often you need to go back and make a change to something you did weeks ago in the design process. So one of the things the 3D tool has to do is maintain the history of how you got to the design so you can change it. And I'll show you examples. It has to manage the complexity and typically include ways to collaborate. There are multiple ways to represent 3D geometry. The most common is called BREP, where you represent the surface. FREP describes functions. VREP represents volumes, and we'll see examples of each. When you begin, you do it with graphical interfaces. You click and drag. But as you progress, you'll be doing more coding, where you write programs, not just clicking and dragging. And then there's a sequence. Imperative is where you design what you want, which sounds obvious. Declarative is rather than designing what you want, you describe what you want it to do, like a table to carry a weight. And then the design tool figures out how to meet what you want. Generative is rather than clicking and dragging, you use algorithms to generate the design. Optimization is where the design tool helps solve like how to make a strong structure with a minimum mass. MDO is where you optimize over many different disciplines. So heat transfer and fluid mechanics and structural mechanics. And then finally AI, which I'll talk about at the end, builds on all of that. And so as you progress, you'll move from just clicking and dragging to these more advanced design tool supports. So There are beginner tools like SketchUp and Tinkercad. They're fun, friendly, easy to use. I don't recommend them just because there's a real limit to what you can do with them. You really need a full feature design tool. Blender is an interesting special case. Blender started as it was a computer graphics house in Amsterdam. It became a startup that had funding to commercialize its tools. That didn't work. They open sourced it. It became a foundation. Its roots are in graphics, in making beautiful rendering and animating. It doesn't have a strong geometry engine historically, but more recently it's developed what are called geometry nodes that let you program geometry. And this is work on CAD extensions for Blender. And so all of that is maturing. And so, let's see, this is an example in Blender of sculpting. So I've got an object. I'm going to subdivide it. I'm going to render it smoothly. And then now it's like a lump of clay. So what I'm going to do, and here I'm using a symmetry constraint. I'm tugging on it. I can pull on it. I can stretch it. And Blender is particularly good at this kind of modeling, at like smushing and stretching. Um, so that's sculpting in Blender. Then Blender has great tools for real-time animation. So I'm going to put some objects into a scene. I'm going to turn on the real-time renderer. It has a few different renderers. And then I'm going to go into a materials library and I'm going to give material properties. And then I'm going to do an animation. And there's many different ways to animate. One of the most common ways is just keyframes. So I'm going to pick keyframes and I'm going to adjust the parts. And now I've made a movie and I can, a little movie of the ball bouncing. So I'm lighting, I'm rendering, I'm animating my scene in Blender. And then I can export to a higher quality external renderer. So Blender is improving for CAD, but we'll talk about a number of other CAD tools, and it's a great choice for rendering and animating. And we'll talk about physics shortly. I'm going to talk about physics in today's class, and there was, during the instructor bootcamp, in the chat is a link to using the geometry nodes, where you describe geometry as what's called a data flow graph, a graph of the steps to construct it. ZBrush is a commercial tool, a powerful tool to do the kind of sculpting I showed you. Rhino is popular with designers, and Grasshopper is data flow for that. That's commercial. And then now we get to FreeCAD, Fusion, SolidWorks, and Onshape. Fusion is from Autodesk. XDesign and SolidWorks is from SolidWorks, part of Dassault. Onshape is from part of PTC. These three are commercial tools. FreeCAD is freely available, open source. They all let you do what we're going to cover in the class. FreeCAD wins for being freely available, open source. You don't need a license. You can install anywhere. The other three, we've arranged licenses for you, but they are commercial tools. Fusion has generous educational terms, and Fusion is perhaps the best integrated end-to-end for all the steps of designing, rendering, simulating, and sending for manufacturing. SolidWorks is perhaps the best at complexity, at industrial strength, handling really complex designs, and XDesign works in a browser. And they have a generous maker offering. And Fab Connect is collaboration we've done with them of connecting the tools into machines. Out of all of these, Onshape is most like Google Docs, if you're familiar with that. That was designed from the ground up to live in the cloud, in a browser, in collaboration. So there, you're not running a local design tool. You're working in a shared design space. And I'd say that one wins for collaborative support. But now what I'm going to spend a while on is all of these can do everything I'm going to show you now. I'm going to show you the examples in FreeCAD, which is the freely available option. FreeCAD is based on workbenches. So each of these is a different task you can do, and the workbench reconfigures all of the menus and options. And there's a number of workbenches built in, but it also has many, many workbenches contributing that you can install. This is a particularly important one I'll be talking about, the assembly workbench. So as an open project, many people are contributing interesting workbenches that extend it. So this is just showing some workbenches I like to use. So I'm going to go through a series of things full-blown CAD needs to do. So snaps are ways to align things. So right now, these are 3D objects. I'm viewing it in 2D. And initially, I can move an object however I want. But I'm going to go to a snap menu. And so one snap says I should snap to the grid. So I should only move on to grid points. This snap is saying I should only move horizontally or vertically. That snap says I should align with edges. The snap I just did is aligning with vertices. You can snap to many different ways that limit how you move, that help you align. When I make an object, it's there graphically. I can manipulate it graphically. But crucially, each object has a data record associated with it. So I can go in and I can edit the data associated with the object. So here, instead of clicking and dragging, I'm using the data interface. And then what I'm doing now is I'm making a part, which is a container. And I can put objects into a part, and then I can manipulate that together as an object. And then here, I'm going to vary where is the origin of the container. And that adjusts when I rotate an object, what it rotates around. So the container has a different origin than the part in the container in that example. And now I've got multiple parts in my container. So that's just coordinates and containers. Now, one of the ways you can do 3D design is you design in 2D and you promote to 3D. And there's multiple ways to do that. So here I'm going to make a curve in 2D in a drawing tool. Then I'm going to go into a part design and I'm going to extrude. So I'm going to stretch it into a 3D object. Another way to do it is a revolution. So here I'm going to make a curve. And I'm doing what's called a spline, which is a smooth curve. Then I'm going to spin it around, and I'm going to make a bowl by spinning my curve. So that's a revolution. Lofting is very powerful. Here what I'm going to do is I'm going to make a cross section. And then I'm going to move in Z and draw it. In 2D, it looks the same, but I'm drawing it further in. So if I rotate, you'll see those are displaced. And now I'm going to loft, which pulls a surface between these cross sections. And I've just got two, but I can have, for example, making a boat, you can have many cross sections along the profile of the boat. So that's lofting. Sweeping is where you pull a shape along a path. So let's say you wanted to make a faucet for a sink or a bicycle handlebar. So I have a path. Then I'm going to place a shape. And now I'm going to sweep the shape along the path to make that. So far, I've been going from 2D to 3D. Constructive solid geometry, or CSG, excuse me, is doing logic, what I call Boolean operations, but on shapes in 3D. So here I've got a torus and a cube. I'm going to take those two objects and I'm going to do a difference. So I subtracted them. That's like what I did in GIMP and Inkscape. But the difference now is I've subtracted them, but they're still there. So if you look, you can see the torus and the cube in the history. And I can go in, and now I'm going to edit the torus, or I can edit the cube. And if I edit the original shapes, it propagates through the CSG operation. There, I'm going to do the Boolean in the opposite order. I'm going to make my shape transparent so I can see into it. Or I can find where the two parts intersect, where they meet. So that's constructive solid geometry, doing logic on shapes. And in a full 3D environment, when you do logic, the parts don't disappear. They're still there, and you can edit the parts that go through the CSG. Symmetry is helpful because I'm going to talk about trade-offs in a moment. Often parts have symmetry, and so it saves you work to only design part of the part and then use symmetry options to do the rest. So I'm going to make a shape. I'll extrude that. Then I'm going to take that shape and I'm going to mirror it. So I'm going to flip it. and I can control the angle of where I'm mirroring it. And then if I go back to the base shape, right, I'm going to connect those into a single object, and I'm going to mirror that object. So I just did a Boolean to connect them, and then I just mirrored them. So I've now got all of this. Now, if I go back to the original sketch and I edit that, it propagates through all of those operations using the symmetry in the design. Next is padding and pocketing. So here I'm going to, this is a workflow where I start with a sketch or a shape, then I pick a face. And on that face, I'm going to do a drawing. So I'm drawing on the face of an object. And then I can pad that to extend it out. Now I'm going to take this face and I'm going to draw on that face. And then rather than padding, I'm going to pocket it, which is where I drill into it. And so this workflow where you sketch, you promote to 3D, and then you draw on faces, and then you pad and pocket lets you very quickly make all sorts of complex geometries. Filleting and chamfering is very important. At sharp corners, there's stress concentration, and that's where parts often fail. So what I just now did is I smoothed all of the corners and all of the joints with a fillet, or a chamfer is a facet. And both for strength and, for example, for how we fit parts together, those are going to be important operations. Offsetting, we're going to have a lot of use for. Offsetting is inflating or deflating an object. So I'm going to, here I'm making it bigger, or I can make it smaller. And in a number of different fab processes, we'll need to do that. Next comes something really important, which is hierarchy. So if you design a jumbo jet and you've got fasteners and you decide you need to change the fastener, you want to instantiate one fastener in many places. So what I'm going to do is I'm going to make links. So here I've got a shape. I'm going to use the cylinder to do cutouts. So what I'm doing is I'm making links, which are many copies of the cylinder that stay connected. So now I'm going to position these for where I want to make cutouts. And I'm going to do a Boolean. But because those were all cloned, I can take the original cylinder, and if I edit that, all of the linked cylinder changes, and that goes through the Booleans. So that's linking in hierarchy. You can do constraints in 3D. So here I'm going to do CSG. Then I'm going to draw on that face. And this is something fairly non-trivial. What I'm going to do is I'm going to bring in the edge of the Boolean into my sketch. I'm going to make a drawing, but I'm going to say my drawing, I want it to touch that edge. Then I'm going to use it to make a cutout. And now I'm going to do something very non-trivial. I'm going to edit the sphere. And when I edit the sphere size, what just happened is the sphere changed. It went through the Boolean, that ball became smaller. It then went to the sketch where I said I wanted the cutout to touch the boundary of that. And then it went to the cutout from that, and that updated. And so all of that propagated through using constraints. Construction is, you can, in your drawing, you can make things that are used in the drawing but not visible in the final design. And this is very powerful. So I'm going to switch into construction mode. So I'm drawing lines, and you see these are blue. They're not part of the final part, but they're helping me describe constraints. So now what I'm going to do is I'm going to take those, give them an equality. And now this part is automatically centered because I'm using those construction features. Projections and sections. Often we want to make a 2D slice of a 3D object. So I've got a 3D object. And what I'm going to do here is I'm making 2D projections, projecting onto a surface, the 3D object. Or I could do a slice through the 3D object. So I'm going to take my object, and this lets me take a slice through it. I'm going to turn it off. And now I've got a 2D path that's a slice through the 3D object. Alignment is registering things, but you can do it in 3D. And so here I'm going to use an add-on that adds a tool. And what this lets me do is take faces and say, I want these aligned. So I'm putting all these parts together with an alignment tool. Okay. Then this next example is something that was originally missing as one of the most powerful tools in FreeCAD, and it's assemblies. So I'm using the assembly workbench. I've got these two parts, and assemblies are like a 3D analogy to what we did in the 2D drawings with constraints. So I've got these two parts. I can take, I'm now making an assembly. So I'm going to make links to my parts. I'm going to put them in the assembly. Now I can take a part and I can just move it and nothing else happens. But now what I'm going to do is I'm going to take those two curves. Then all of these are notions like be centered, faces touch, edges touch. You can describe all sorts of 3D relationships. So here I'm going to say I want them coaxial. I want them on the same axis. And now if I take that part, if I move that one, the other one automatically adjusts. If I change the angular position, the assembly automatically updates the other part. And so this is essential. You'll be using assemblies as you build parts together. Measurement is often, with all this constraint solving, it's finding the geometry, and so you don't even know what it is. So measurement tools let you go in and measure sizes. and get, rather than you giving dimensions, if it's solving it, it'll tell you the dimensions it found with the measurement tool. So that's measurement. Folding and unfolding. One of the places this gets done is for working with sheet metal. And so what these tools let you do is I'm going to go into a sheet metal mold, and I'm going to start building on the faces. So I now made a little cube, but the key thing I can do now is I can flatten it so that I could cut this out on a 2D tool, and then I can fold it up into the 3D shape. So that's folding. Now I'm going to descend deeper into being parametric. We showed a simple example with the dimension, but often you need to do math with formulas and you have many variables. And so we're going to do that with a spreadsheet. So here I've got two shapes. I've got two spheres. Now I'm going to add a spreadsheet. So this is a table. And in this table, I can put words like radius, a human readable word. I can give variables names. So I'm going to name a variable, the radius. Now I'm going to go back to my drawing. And remember, we can edit the units, the dimensions, but you can edit the dimensions with variables. So I'm going to go in, I'm going to say, I want to use a variable in the spreadsheet for the radius of the sphere. So now if I edit the spreadsheet, I change the size, the spheres, but it doesn't move them. So now I'm going to go into the position and I'm going to use the position, also a variable, and that's going to be twice the radius. So I'm doing a little formula. So now when I edit that one variable, the spheres change size and they change position. And so that's the key of building a parametric design where you have name variables that you use throughout the design. Everything you're doing in FreeCAD is actually sitting on top of the Python programming language. And you can open a Python console and you can see every option you do is a command. And you can come down and you can write commands there. And so in this example, what I'm going to show is you can use the Python console to access the data structure in your design and modify variables in the design by writing little tiny bits of code in the interpreter. So everything you're doing in the graphical interface is actually happening in this window where you can see what Python is doing, and you can put commands there. And in particular, after that, you can write little programs that access everything. So there are a lot of these shared. And so I'll show two examples. So this is a little program that creates gear designs, which is a surprisingly subtle thing I'll talk more about later. And you can open it up and see this is what the code looks like to do that. And then this next example you'll see is to make a honeycomb. And so with that little bit of code, it made all of these shapes. It would be a lot of clicking and dragging to do it, but it was very easy to do programmatically. Leo's asking about OpenSCAD. FreeCAD has an OpenSCAD workbench in it. So you can merge OpenSCAD with FreeCAD. I'll talk about that in a moment. Okay, we're almost done. Here's a part. I'm going to go into a drawing tool. So for both handing work off for documenting it, often you want to represent it in a variety of ways. The drawing tool lets you take your design, bring it into a page of drawings. So here it's doing a line drawing of my 3D shape, and I can choose all sorts of views. So here I'm picking the direction I'm viewing from. So it's a 2D drawing with a projection of the 3D object. And here what I'm doing is in the drawing, I'm doing a slice through the 3D object. And then all of these 2D drawings, of course, update if I go back. Yeah, I'm going to show that. If I go back and I edit the 3D object, it propagates through the drawings from it. FreeCAD has a rendering workbench, so you can give properties to an object. And then, so here I'm assigning different materials to different objects. And then it sends it out to an external renderer. It's not as powerful as the other rendering workflows, but you can do it. It has an animation tool, again, is not as powerful as the others. So you're going to need all of these skills to do full-blown CAD. You can do all of that in FreeCAD. There's been a recent fork of FreeCAD on sale, which is a number of developers building a polished version of FreeCAD with stronger tools built in for things like assemblies and commercial support for collaborative platforms, but based on the open source lineage of FreeCAD. So again, to recap, FreeCAD is great if you like open source tools you can run on any computer. You don't need an identity. Then we have licenses for Fusion. I'd say Fusion does the best job, just recapping, of CAD and then simulation of mechanical properties, rendering of how it looks, and export to CAM is nicely integrated. SolidWorks is really good at complexity, that all of these tools break when designs get too complex. SolidWorks and then XDesign essentially is SolidWorks in the cloud, is really good at, is only in a browser and is really good at collaboration. Let's see, question about human character modeling. That's Blender. That's right in the sweet spot of Blender. You'll find all kinds of gorgeous rendering of Blender modeling people. Blender does gorgeous character modeling if you browse Blender galleries. A few other tools. These are commercial and industrial strength tools. OpenSCAD is a hardware description language, where instead of clicking and dragging, you write code. There's a version of that that runs in a browser. And then there's an open SCAD workbench in FreeCAD. This is a series of tools written by a former student to do functional representation, where you make a data flow graph, and then it's describing the object not by the surface, by the function in the interior. And so that lets you do things like interpolate. So what it's going to do here is I'm going to make a shape between two shapes, continuously interpolating between shapes. That's the sort of thing you can do with a functional engine. End topology is a commercial tool, support with it. GrabCAD is a platform for sharing models, and GrabCAD has a viewer. Oh, it looks like the link is broken. I'll fix that. GrabCAD is one of a few viewers that let you build 3D assets in a web page. So next week's assignment, you're going to need to do a parametric design. And so for this week, you should pick one of FreeCAD, Fusion, SolidWorks or XDesign, Onshape, or OpenSCAD. They all let you do parametric design to be ready for next week's assignment. And my recommendation is asking which one is best is like asking who should I date? Who you date is very personal. And the design tools are very much like that. Every one of these have people who love them and people who hate them. It's a very personal choice. I would recommend sampling each of them and finding which one works for you. Interchange formats is when you move designs between these, information is often lost. We'll use STL just for raw geometry for printing, but it's only triangles. OBJ we'll use for color. Stay away from Aegis, but STEP is a pretty good interchange format that you lose history, but it lets you move designs. McMaster Carr is a place we buy parts from, but anything you could buy from McMaster Carr comes with a CAD model. So that's a really easy source of CAD models. FreeCAD also has libraries of models. Unreal, Unity are commercial game engines. You make video games in them, but they have free versions. Godot is an open source one. These are designed for making video games, but they all include modelers to build assets for the game. And so if you you could do all of your work in them. These are a growing group of tools which are designed for sculpting in virtual reality, where you can't do it looking at a 2D screen, but you go into a 3D environment and you sculpt in the 3D environment. These are then modeling tools. This is a link to a class I teach on the math of modeling. Blender has a physics engine that's very powerful. So here what I'm going to do is I'm turning on the physics engine. I'm telling it what kind of physics I want to use. And the simplest physics is rigid body mechanics, just hard objects. But it also knows how to do soft objects. It does fluids. It does wind. It does fabric, many different kinds of physics.
Hello, Neil.
Yeah.
Hi, this is Greg Weiler. I'm here with a bunch of the teams in Benin, and STEM Inspires, my daughter's nonprofit, is doing, you know, First Robotics, right?
Yeah.
Yeah, so she's building with Prudence here, who runs the country. They're building 25 teams here, First Robotics teams in Benin, and 135 teams in Rwanda. And I just happened to be here visiting his lab, which is incredible. They're signing it right now. They're signing an agreement with City right now, over by, the printers. So I just thought you were on here, and I've heard all about the Fab Lab and stuff, and they're building a lot of stuff in Rwanda right now. So I thought, why not take the opportunity to sail out?
Good. Okay. Thank you for introducing. Glad to see all of that happening. Exciting to see what's happening in Benin and Rwanda.
It's an enormous amount. So you got to encourage this guy to keep on getting more people. Have you been to this lab?
Here, we need to keep going in the class. This is a bad time. Once the class is over, we can chat. But thank you for introducing.
I'm online. Maybe they can text me in inbox.
Hey, Greg.
Okay. Good. Once class is over, we can continue the conversation. Thanks. Okay, so what I'm going to do now is I'm instantiating multiple objects. Now I'm going to turn on the physics engine. And it's going to be kind of disappointing. Everything just falls because there's gravity. But now what I'm going to do is I'm going to nail one of the objects down so it doesn't move. And now if I turn on the physics engine, now the chain swings. And then I'm going to jiggle where the first object is. So you didn't have to animate and script that behavior. That behavior came from just taking your design and turning on the physics engine. And so there's all sorts of ways you can simulate your final project by picking all of these different types of physics and then simulating it. This is not physics simulation that is carefully calibrated against reality. So you can't use it to decide if a bridge will hold up or fall down. It's more qualitative physics for perception, but it does a beautiful job of simulating physics. These are then, FreeCAD can talk to a finite element solver that does let you do quantitative prediction. Elmer is an open source multi-physics simulation environment. Here. I'm going to unmute if you need to talk. Elmer is a open source version. COMSOL is a commercial one. These let you do all kinds of physics. So they let you do heat transfer, electric fields, magnetic fields, fluid flow quantitatively. Fusion has powerful mechanical simulation built in. SolidWorks, part of the ecosystem of SolidWorks is Simulia that has Abacus that's very high end, and SolidWorks simulation is a powerful tool for simulation with that. Okay, a few final things. You're going to be making audio and video clips. Yeah, there's a note to OpenFOAM for CFD. Audacity is a freely available cross-platform tool for editing sound. That's what I like to use. For video editing, there's a number, this has gotten much better. These are all open source, cross-platform, freely available nonlinear video editors. I use Kdenlive. It's really matured. So these let you take video in. You can edit, composite, do all sorts of transform, layer, track, edit, make transitions, and then render out in all sorts of formats, and add credits, titles, captions. And so these are open source tools. These are commercial ones. You'll need one of these to edit video. Then FFmpeg is like ImageMagick, but for video. So it lets you convert and edit any format to any video format. MPlayer and VLC are open cross-platform media players. Different platforms are proprietary for what sort of media types they accept. These play any possible one. And now we get to a really important thing. HTML5 extended the web with video. there are particular formats it allows, and this was the error we saw earlier in class. Only some formats can play in the web without plugins. And so here's a cheat sheet. So MP4 is widely supported format for video. It does good compression. Sort of think about it like JPEG for video. Each of these is an FFmpeg command. So this takes your input video, whatever format it's in. This says I want H.264 MP4 codec. This sets the quality. This sets the resolution. This sets the audio. This version varies the bit rate based on how much is happening in the video. In some cases, that works best. This one makes a fixed bit rate. This is making bits per second where you're setting the bit rate. And again, you can separately set the size of the image is separate from the bit rate, which depends on the amount of compression. This makes a video without audio. You can use this to crop the video. This trims where you start and stop. This can mix different sources of audio and video. This actually does complex editing where it crops, pans, and composites all in a single command line. This is a really important one. This takes a series of images and makes a video. So GIF is a format you can use for multiple frames of moving video, but I don't recommend it because it does terrible compression. This, if you want to show like stop motion, this takes a series of images and compresses them to a video. So compressed, your videos should be on the order of megabytes a minute. When you take the raw video, it's likely to be much larger and not play in a browser without a plugin. But with this cheat sheet, you can compress video down to on the order of megabytes a minute. That's the video compression. Sorry, something's gone wrong with, okay, I'm not sure what just happened with the browser. So that's audio and video compression. OBS Studio, I'll just mentioned, is a really powerful tool that lets you run a whole studio where instead of just a webcam and a camera, you can in real time feed multiple sources in and switch and move around among the sources, both live for things like what we're doing now and for producing your videos. Question in the chat about version control for 3D design. Some of the 3D design formats do human readable formats where Git knows how to version them. But key for that is all of these design tools, almost all of the design tools I showed you have a notion of versioning and history. So each of them has their own way they store and share designs from it. But within that, you version not at the level of the file format, but at the application level, that the design tools have notions of how to do versioning. A final note on AI, Midjourney, DALL-E, Stable Diffusion, all let you make 2D images. And you've seen lots of examples in the memes. The one caution to be aware for them is something that's rapidly changing is copyright. Often the images they're doing infringe on copyright. The legality is evolving very, very quickly. In 3D, these are all versions of the large language models for AI natively don't understand 3D geometry. These are all versions of AI systems that do understand 3D geometry. And this is a paper written by colleagues that talks about using large language models to do CAD, where they do an interesting job of asking large language models to do 3D CAD designs. Let's see, I'm going to, let's see, this browser has is hanging. Something's not right with the browser. So CAD is rapidly evolving. We'll be doing the recitation on CAD. We're going to have CAD students doing the homework of the class. You can use CAD tools in the assignments, and what the CAD tools can do is rapidly changing. The important thing, though, is like any source of information, any use of CAD tools, you need to acknowledge, and you need to mention use of CAD tools. So wrapping up, no recitation in the coming week. The week after that, we'll do a recitation on AI. And then, yeah, so parametric, yeah, let's see, lots of questions in the chat. So, version, yeah, so Daniel is asking a key question, which is any of the full-blown design tools I described maintain either a tree for how your design is made, or they made a history of the steps you did, but all of them let you go back and do something you did many steps ago and change it and propagate back through the design. That's one of the key things all of these design tools do. Parametric design, for that question, is if you think about the construction kit, you're going to be making a construction kit. There's going to be a joint design where you have slots and you're going to have chamfers, and there's different shapes for the joints, and there's the dimensions that those are going to depend on the materials you're using. And so you need to enter parameters like the slot depth and the slot width as variables. And then when you change that variable, your design completely rearranges around it. And so in FreeCAD, you do parametric design by introducing a spreadsheet. And each of the other CAD, full-blown CAD tools I showed you have ways where you introduce variables. But if you go back to the example, remember in the spreadsheet, I had something called radius. I used that variable, and then the radius changed in my spheres, but I used it in a formula to move the position. That's what you need to be able to do. And so for this week, I would, in your lab, experiment with all the tools, see which one feels best to you, see what makes sense, and then make sure this week you understand how you use variables in your design so you can edit the variable and propagate it through the design. And for next week's class, we'll need to do that. Okay. Any final questions? Let's see, a question about WebP format. Web is they're all fine. JPEG has been around forever. PNG is also mature for uncompressed versus compressed. WebP is a more recent format. It's widely supported in browsers. It's potentially does better compression. I don't have a strong reason to choose it over the other options. It might, I believe it can do better compression because it's a more recent format. Mohammed's asking about Fusion. Yeah, so you'll find in the class, there's going to be groups using Fusion and SolidWorks and Onshape and FreeCAD, and each will be very passionate about why that's their favorite tool. I think I don't have any one-line recommendation for any one of them, other than, once again, try all of them, and then there'll be communities using each tool you can compare notes and share with. Okay, so yeah, this week, focus on breadth, on trying as many tools as possible. And again, in particular, I want to see 2D designs. You can start from sketches, raster vector. I want to see 3D designs. I'd like you to make rendering, which each of these tools can do. See if you can animate or simulate operation of it. Just try to find as many different ways to represent your designs. And then most important is focusing on the parametric design. Muhammad is asking on his website, in this class, there's hundreds of people, so it's not good for me to do a one-on-one question like your website, but each of you have a whole hierarchy of support. In your lab, you have students and instructors. In most parts of the world, we're doing regional reviews where you can meet regionally. And every Saturday, there's the open time. And the open time is a great occasion for, if you want to have a review of your website, if you have questions of your website, the open time is open for any possible question. In class, I like to keep the questions focused on what we did in the last week. Saturday open time is for anything you can think of. Okay. Okay, we're up to the hour. So I'm going to stop recording, and then later the day of class, I'll be posting the video. This is a fun, expressive one. I look forward to see what design tools you use and how you express yourself with it. This will be a fun class to review next week. So once again, in each of your languages, we all say goodbye. Bye-bye.
Bye.
Adiós.
Bye.
Ciao, ciao.